Hello and welcome back to the stream. So in the last couple of streams, we added support for arrays. We're able to declare arrays of an arbitrary compile time size and then access them. And the plan for this stream is to add this braced initializer so we can properly initialize our arrays on declaration. So there is something curious about the way this is specified formally in the standard. So in our AST, we've got an expression, and every expression has an associated type. But a braced initializer, so when we put like this thing here, it doesn't actually have a type. This is because it's not an expression, it's an initializer. So the standard says that here in the declaration, if you have an init declarator, we've got something, then an equal sign, and then an initializer. Crucially, not an expression. And initializer is either an expression or a braced initializer. And so the first thing that we need to do is we need to add some support for that. So currently in the parser, when we are parsing a declarator, we are parsing so somewhere we're parsing an init declarator, I'm assuming. Init declarator right here. So we're parsing a declarator, equal sign, assignment expression. So this is something that we need to change. We need to pass an initializer instead, which can be an expression or braced initializer. So we've got the init declarator right here, which contains an expression. This needs to change. So we need to add an initializer. Let's do it. So declarations themselves already have initializer, so we need to add something. Let's add it right here. So the initializer of a declaration. So we either want to store an expression, a single expression, or a braced initializer, which essentially consists of, so it can be empty, or it contains a comma-separated list of, let's ignore designators, for now, a comma-separated list of initializers. So we got some sort of tree structure, which means it makes sense to add a new kind to our tree. So we've got initializer. This is an abstract node range. It is yeah, let's make it always a container. So every initializer. So does every initializer does make sense to turn everything, because the single one, let's just make it a container of other nodes. Yes. Let's just make that. And then we've got node kind first init, node kind last init, which we obviously need to define. Node kinds. So we've got expressions, we've got statements, now we've also got initializers. So we've got I wonder what the best way to structure it. So the grammar protection special case is the empty one, but I don't think it is. Oh, it actually is special cased, empty initialization. So let's also specialize it in the AST. So empty init, braced init, and expression init. So the first init is the empty init, and then the last init is the expression init. Okay. Yeah, and let's also call you then init. And let's keep the container. So that is and I don't think it has any specific members. So I believe there's a macro to define like the sort of abstract base class in our tree hierarchy, and we're at abstract node constructor init. Make it protected. Okay. Yes. Okay. I have to, like, it's been so long since I wrote something about that. Yeah. Okay. So the empty initializer. Empty init. This is a basic node. Yeah, that's the interface. Okay. So this is a node of kind empty init, inheriting from init. And it doesn't have any data. So we just add the constructor. Okay. A waste initializer. Likewise is a basic node. Waste init. And this one has children. So we write a constructor waste init. Node constructor. And then we get unlinked node list of its children, which are themselves initializers. We pass that onto the constructor, and then we insert child list after the beginning. Initializers. Okay. And then an expression. Initializer is the last one. Expression init. Okay, so the difference between C interpreter, between like a script that calls the compiler and executes it, is fundamentally, so first of all, the interpreter, it's quicker to interpret something than to actually execute it. So when you like for example, Clang takes a long time to compile the code, and by the time Clang has compiled it, we've long executed it for like very simple snippets. And then the other thing is the nature, because I'm writing an interpreter. It's a memory save, so I can do like checks to query whether or not a pointer is still valid before I can dereference it, and then I can generate like nice message instead of segfaults, and so it's a safety thing. But mostly like I have the interpreter library lying around that I wanted to test, so I just needed something, and I thought writing a C interpreter might be a cool thing to test it out. But okay, so an expression initializer. There's an expression init, inheriting from init. And it has the actual expression as its member. Expression init, node constructor. And then we get the expression. And actually don't need to store it, I can insert it as a child. So the child of an expression init is the single expression. So it's the first child. Okay. Now let's actually take you into an own section, just to make it nicer. So okay. So now the variables and so on, instead of having an expression initializer, they have an init initializer. Init initializer. Init initializer. Yeah, variables are the only one that have an initializer. The rest doesn't. So let's see what sort of compiler errors we have. Right, enumeration values not handled. So let's handle them between the statements. So case cout node kind empty init, waste init, and expression init. Now matching function to calls the constant eval, right? So we've got code for constant evaluation of the initializer of a global, but that's no longer an expression, that's an initializer, and we need to handle things accordingly. So that also means that we can no longer ask the initializer for the type because a braced initializer doesn't have a type. So we need to pass in that type. Like so. And then before implementing it properly, let's just assert that we're having an expression. And then I worry about how we can implement the braced initializers. So nodecast develop expression init expression. It actually makes sense to give you a setter, so a getter, so we can get the expression. Now let's spell that out. Expression return first child, and we can safely downcast it at this point. And then make it const correct. Okay. Like so. And then we pass you the type of the thing. Okay. And then converted init at this point here is an expression, because we need to adjust the init declarator as well. It does not takes an initializer and not an expression. And then this function as well. Now matching function. Okay, so here we're doing a conversion of the expression to the appropriate type. This is of course only necessary if we are having, because a braced initializer doesn't have a, then we would also need to do, what does the standard say? How does it get converted? Semantics. Unnamed members. It's not initialized. Right, this is default initialization. The initializer, an array, each brace has an associated current object, right? And then we initialize it recursively or something, right? Okay, let's just implement it for expressions. Let's worry about that once we get to it. So the converted init starts out to be the initializer that we specified, and if we're having an expression initializer, expression init, then we need to do an assignment. So casted expression. So we convert the expression to the appropriate type, and then we convert the converted initializer to, so then we want to create a new expression initializer for that expression. That's a bit tricky, because due to the API, when we have the So I can't. So the thing is, this modifies this expression in place, which isn't possible if it's already part of the tree. So I can't make you the child, and instead I will need to store it. Which isn't a problem, because then it's not yet linked into the tree, and we can modify it. And then we can also just add a setter. And this is the one that we're then calling here set expression to the casted expression. Right, and then here we're checking whether or not we're having a constant expression. And instead of checking whether we're having a constant expression, we need to know whether we have a constant initializer. So this is, I'm guessing, so we need a function bool is constant initializer. Yeah, it's called a constant init. It gets an initializer. And what it's doing is it essentially recursively checking. So we are visiting all potential things it can be. If it's the empty initializer, then it is constant. If it's a braced initializer, then all children need to be. So child in init children. If not, it's constant init child, return false, otherwise return true. Right. So here the children have the same type. Not have the same type because this is not a container of nodes, but a container of other initializers, which we can't do yet. So we need to do your generic node, and you are a container node. Base class for all nodes that aren't child nodes. Yes, and then I need to essentially pretty sure there is a function child nodes. Right, that one. Child node range getter, yeah, something like that. So braced init, and then we want to get all inits, initializers, null pointer, last child. I'm not sure what's the last child. Can I just nets? Yeah, I think that one. Okay, so now we can get all the children, which we can use in where was I? It's constant init, right? So we initialize the initializers. Yeah, sure. Let's use all of. If you insist, so return all of. I don't want an execution. Yeah, you know what? I'm not bothering with it. Okay, and then finally, when we have an expression in it, then we just delegate to the expression version. So it's constant expression of the initializing expression. Right. And now we can query. Right here is constant init instead. Right, and then here when we construct it, we give you an expression and not an initializer. So the init declarator passes an initializer. And the standard says an initializer is an assignment expression or a braced initializer. The braced initializer is essentially a comma-separated list, which can be empty, of other initializers. So that's easy to parse. So we've got a curly bracketed, potentially empty list of initializers separated by comma, and we're allowing a trailing comma. Or if it's not a curly bracketed list, then we're passing an assignment expression. Okay, and that gets converted into so we've got the as list. Does it work parameter? Yeah. So if you're having a list, we're converting that into a unlinked node list of initializers. Which then feeds into a callback that returns a new initializer. And I believe we can, yeah. And we've got two cases. So either we are getting called with our compiler state, and then an expression. And if that's the case, we want to construct a new expression in it, initialized by that expression. Or we're getting called with the unlinked node list. Of inits, and then we're having a braced initializer, and then we need to decide between two cases. If it's so if it's empty, then seal of empty init. Otherwise, braced init of the thing. Okay, and then instead of passing an assignment expression, we're passing an initializer. Now, why is that one not, why doesn't the compiler like that? Right, we want a location to construct the thing. No problem, so let's get a location first, and then we are passing the thing. So now we're getting the position as well, which we can then pass to the constructor. Incompatible operator types, empty init and braced init. Yeah, but you share a common base class. Okay, so let's do that. And you want to return. Okay, so we are still getting the error from the constructor. Alright, because we are no longer getting an initializer, an expression, we're getting an initializer, which we can then pass to the thing. Okay. Right, and then we need to handle the initializers in CodeGen. So we're handling them here a bit, not the braced ones, only the other ones. But when we then create a local variable variable declare right here, we are visiting the initializer, which currently does nothing since we are ignoring it. So initializers. So if we are getting called with an empty init, we are doing empty initialization. What does empty initialization do? Let me guess, that is somewhere at the end now. So this is called empty initialization. Is that term actually used anywhere? Apparently not. Right here. Same as in initialization static store iteration, so essentially where we want to zero it out. So we're just pushing a 0 here. This is going to break as soon as we have more complex type, but at the moment we don't. So let's just push 0. So the thing is, like, we need to push the 0 of the appropriate type, which might involve pushing multiple zeros. So we can't do it with visiting, not really. Yes. So we need to write an actual function that takes care of them. So let's write a function. Initialize object. Clog init. Right. And then the type. Okay. So initializes the object whose address is on top of the stack. Right, that makes sense. So if the thing, so there's a simple case. So we've got this. So if we're having something like an int, then we can initialize it with a single store. But if we have an array, then we need to initialize it with a loop of sorts. So initializing it, like, we need to check whether we can, like, essentially need to check whether we have a type. I have CodeGen type right here, which right. It's not supported for array types. So let's make them the following. So CodeGen a type. Let's return a pointer, so we can optionally return null pointer if it's not the type that we can natively initialize. So return null pointer. And then we're also returning null pointer for arrays. Okay. So, and then we can do the following thing. We need to make a distinction if we have a native type or if we don't. So, if love type. So if we're having a native type for the C type, then we can initialize it using the instructions provided by love. So we're visiting all possible instantiations of that thing. If it's an empty initializer, we can initialize it with 0. So we're pushing 0. Then we need to do swap. And then we can do a store. Using the loaf type. Okay. Raised init. Let's make it to do for that one. Unimplemented. And the expression init. For that one, we are performing code gen for the initializing expression and then storing it into the field. Actually, we need to store the field another way. Okay, so push the value, evaluate the initializer to a single stack value and store it into the object. Else unimplement. Okay, so just to get the tests pass. Now if we return the pointer, so I need to adjust a couple of things. Cannot initialize with type. Oh, right, we want a const pointer. And then we need to dereference a bunch of things. And once we have that, actually we don't need the type here in constant devar, we just need the layout. Okay. And almost there, I'm guessing. I'm hoping. Okay, and yeah, so now we just need to call this function when we initialize a variable. Code gen initialize object context type initializer, like so. So we are loading the address of the thing, and then we can initialize it. Right. Okay, now we're almost there. Actually, let's init object. Let's rename you to CodeGen initializer for consistency. CodeGen init. And we are having an errors in cast global heap. Yeah, okay. So let's try init.c. Let's see where we are failing. We want to traverse. The expression is not linked into the tree. So this error is when they were trying to traverse an expression that's not part of the tree. Right. So let's this is again this I don't like this part of the design that we like, because currently the initializer, the expression initializer, stores an expression as a child member, and this is necessary because we want to manipulate it. But at some point we want to finish it, and then we want to turn it a child of our thing, I think. So it gets automatically picked up when we visit the tree. But for now, like I'm just going to freeze you. So the expression in it actually, so we're storing the initializers. I don't know what's the best approach. Let's just do a hacky thing. So when we pass the init declarator, right here, we are setting the expression. And as soon as we do that, we know that we're no longer changing it, so we can leak it, which marks it the root of the tree, and then the assertion should no longer fail. Right, and now all the tests pass. And when we visit it, this is what I meant, it's not part of the tree. So we get the expression initializer, but we don't see the expression in the tree because we're marking it as leak and not as part of the tree. So ideally, like, it's just child of the initializer node, but then I can't inject an assignment conversion in here. So that design isn't really nice. So what to do? Let's make the following. Just add an API. Let's call it freeze expression. Adds the expression as a child. It can no longer be adds the expression as a child. This needs to be called after all implicit conversions have been handled. Because otherwise we can't inject something else. This isn't ideal design, but it's what I have at the moment. So this means that you contain a child after all, so you're not an init node, you're a container node. Of init, and insert child after null pointer expression of the child. It can no longer be changed. Okay. And instead of calling that, we're calling expression freeze expression. Okay. And that should now work. But so now it's part of the tree. Okay, so that's the basic initializers. What should also work now at this point is we can add, let's make the u. Right, that one actually doesn't compile because waste, it's not an, wow, why are we, that's a root error message. So you should be 0. Okay, something doesn't like that. Let me guess, you're a null pointer. Yep, you're a null pointer. Wait, you're a null pointer of the initializer? Why are you null? that point. So we are parsing an initializer right here. So how do we end up with a null pointer? Actually, let's minimize the thing. So we are just having that, and we want here to be 0. Are we still crashing? Yes. So we're calling this one, and the expression here is null. What? Wait, why are we calling this one? Oh, that's okay. So that's bad overload resolution. So the issue is when we don't have a list, we're not getting an empty node list. So that one's never empty. The unlinked node list. What we're instead getting is Lexi's null opt, and Lexi's null opt is implicitly convertible to null pointer. So null opt need to catch you and create an empty init instead. Right. And now we've got variable decal with an empty init, and the assertion passes, so we initialize it with 0. Okay. So is that one actually allowed? Yep, appears to be allowed. So we need to handle u. Okay, then like the wording is too convoluted. I will just implement what I think is the correct behavior, which is to initialize the single thing with one thing. So this needs to be done when we create here where we do. So if we're having an expression in it, then we can do a cast expression. Braced. So we're having a braced initializer consisting so we need the notion, I guess. Let me actually go to the wording. Each designator list closest to a particular member of the current object. Right, I'm guessing like if the aggregate a union, what are the requirements here? No, for an object not contained within the entity. Like the wording here is really convoluted, but I'm guessing like the idea is that we need to look for scalar types, which are sort of, which we then initialize with atomic, with things, or something. So somewhere in here, right, we've got scalar already as a thing. So if we're having a scalar, then we can only initialize it with a single thing. Otherwise, we need to recursively process the members or something, right? So recursion means we need a separate function. So let's write a function like here, verify braced initializer. So we want to initialize something of a type with a braced initializer. So if the thing that we are initializing, rather, let's call it verify init. So verify init with an initializer. So if the thing that we are initializing is a scalar, then we sort of like need to reach the end of the recursion. That means we're visiting the initializer. If it's an empty init, this is not const because we may need to modify it. So if it's empty, then we're good, right? We can always initialize it with an empty initializer. If it's an expression init, then we potentially need to do a conversion. So converted expression is do assignment conversion. State, I need a location. Assignment op none, I'm guessing. This is the target type, init expression. Location. Okay. And we need to capture things. And then I update you to set expression to the converted expression. And freeze you. Okay. And now if we're having a braced initializer, then we essentially, because we're having a scalar, we must only have one in the braced initializer. So braced initializer always has at least one, so we don't need to check for lower one. So we have one, but we might have more, and if we have more, that's an error. So initializers. So init count is the distance between init initializers begin and init initializers end. If that distance is not 0, we can assert that it is at least 1. Braced init is non-empty, and generate an error. Error, too many initializers for scalar. Primary location here. Right. And then we finish the diagnostic. Otherwise, can I just recurse? So if that one okay? Yeah, it's okay. Okay, nice. Which LSP client? So this is NeoVim's LSP together with ClangD. So because Clang, like, that's actually fine, which means I can just recurse at this point and verify that the the single initializer that we're having itself is already valid. I don't need to worry about keeping track of how many braces we have. So verify the single initializer recursively. And this will then unstrip one brace, and eventually we will reach the expression. So location, type, init, initializers, front. Right. Okay. And then we are calling you. Let's add a to-do. Before I forget. 0 to-do unimplemented. So then we've got this mess right here, where we are instead doing verify init, state, location, declare type, init, initializer. State.file, that location. My language server constantly keeps crashing, so annoying. So Klangly keeps crashing. So where was I? Yeah, right here. State dot input location of the deco. Okay. Like so. Do I actually modify you? I think that should be fine. Oh, too many initializers for scalar. Okay. So first of all, so we're getting it twice because we're calling it recursively for every level. So let's return so we don't get the error message multiple times. Oh, I don't want not equals 0, I want not equals 1. So how many do you think we're having? Why do you think we're having 2? What? Yeah, left cast your motive could help you. So let's ignore that and look at the pass tree. Wait. Okay, it didn't say for some reason. So why do you think we're having 2 children? We're not having a single initial. What? Why isn't it? Okay. So A has an initializer. Why isn't that not showing up in the pass tree? So right here. Oh. It helps if I actually then set the initializer. Okay. So if we actually set the initializer, then it should show up in the pass tree. And we're getting it to do during coaching. Right. Which is annoying because then I don't get the tree. So let's flush you here. Just so we can see the bytecode. I don't want the bytecode. I want to see the AST. But let's flush both of those. Why are we still not seeing things? Let's get rid of this breakpoint. Why are we in coaching? Oh, because compile files too. Okay. Okay, that's annoying. So that one actually doesn't help us. So So the issue is braced. Let me just push 0 onto the stack. Right, so we've got a braced init, a braced init of an expression of an integer constant expression. Right. But why? That's only a single one. I'm probably implementing that thing. So the issue is probably that I'm implementing the braced init because I don't know how to use my own libraries. So you get the last child. Okay, let's write this one ourselves because I don't understand how to use the macro. Oh, I think that's it's a circular thing. So if we pass this as the end one, then maybe that's the correct value I need to pass. Let's add the diagnostic back. And see whether that helped. Yeah, okay. So we are tab checking it, we are just not implementing it during CodeGen. So that was the issue. Okay, so then during CodeGen, line 803. So what we need to do is we need to so essentially we're having a type if and only if we're having a scalar. So let's assert that is scalar type. We only scalars map to single stack values. So then we know that init essentially only has one thing. And what we can do is get the value of that thing recursively again. Right. So let's call a helper. Actually, I can visit. I don't need. I can visit the tree by the init node, and then for init, no need to do anything. The children push the value, and then should just work automatically. Because then we visit the braced init, we also visit its children, which then eventually push the value, and we end up. Let's actually print what we're getting. We're getting 0. And if I put 11 in here, then we're getting 11. And if I make u short, then at some point we are adding a cast expression, and this gets added appropriately passing through. Okay, so that is braced initializer for scalars. We want to do arrays. So there are this to do. So if we're having an array, try cast having an array, and then we sort of need to, again, let's handle worry about each case individually. So init of empty init. Again, that one's fine. We don't need to do anything there. of expression init. Now you cannot initialize an array with an expression, I'm pretty sure. So state logger log of diagnostic count error. Cannot initialize array from expression. Primary location here, and then we finish. And the tricky part again is the braced initializer. So we need to do element check against the array size. So if we are, the issue is if we have not enough, that's fine. They get implicitly initialized to 0. But if we're having too many, that's an issue. So if init count is bigger than the size of our array, then we're having too many initializers. Too many initializers for array. Okay. Otherwise, we essentially need to iterate over each initializer and verify it against the element type. So for auto init in, let's call it element init or elem init initializers, we need to verify the init for the element type. Element type elem init, like so. And that might actually work. To do unhandled non-scalar type. We don't have any at the moment, but we will add structs at some point. So int array of 3 elements, 0, 1, and 2. Let's see what happens. Takes some while to, okay. So we get a braced init consisting of 3 expression inits, 0, 1, and 2. Nice. The bytecode is all messed up because we are hitting the unimplemented case. But that one works. And if I do something like you are short, this will be appropriately, wow, that's funny. This will be appropriately casted. The representation is funny that we're having, like, the one is signed in 64, we're casting it, that's the explicit short that's in the source code, and that's the one that we're adding back to properly initialize the array. But that one works. And if I have too many initializers for array, right? So that one works. Now, if we're having too few, that one should also work. But this is then an issue during CodeGen, because then we need to add implicit zeros. I think a better design is if we then adjust the tree and essentially fill it with like empty initializers as necessary. Yes, that's a good idea. So let's actually, since we're iterating over it, we don't need the distance thing. So let's do it like so. Init count. And then if we're having too many, that's an error. If we're having not enough, I don't need the cast anymore here. So if we are having too little, then let's add initializers at the end. While init count is not the size of the array, we create an empty image. At the location. And then let's call a function that doesn't exist yet. We add the initializer and we update. Let's use this form of a for loop. So we fill it with the necessary ones. And then braced init needs a function to add an initializer. Init I. This insert child after. Like, I wonder how to get the last child. I know how. Initializers. Maybe that one works. Nope. Apparently not. Okay. How do I get the last child? Hello, Langatilla. Are you still alive? Okay. Add initializer. To get the type. Okay. Doesn't know how to get the type. Insert child after. Erase child after. Replace child after. How do I get the last child? So I know that the children range doesn't have, that has the end one. How do I get the last child? So I need to essentially, right, because it's a singly linked list. Because it's a singly linked list, it can't give it, like, we need the one before. So last child. So essentially, like, that's an O of n operation, which we are calling in a loop, so it's quadratic. So yeah, let's actually not do that. So like, we don't want to, because we want to allocate an empty initializer for each array, and if we have an array of like 1000 elements, we would need to allocate. So let's actually not do it that way. So don't normalize it. And then we just handle it in culture. So we don't add it here. Instead, we somehow handle that in culture. So let's write codegen for that. Codegen init. So, unimplemented initializer for non-scalar type. So, if we are having an array, try cast array type, then we need a loop. So we need to loop over each element and initialize it with the appropriate initializer. Now, since the size of the thing is known statically, we can generate that many assembly instructions instead of actually generating a loop. So I not equals array size. Yes, this is our first step. Actually, we need to again visit the tree. Whether we let's do it like so. Okay, so if we're having an empty init, we want to essentially mem set the entire array to 0. Let's just do it by really stupidly by generating a bunch of instructions in the thing. Essentially, like we're doing unrolled loop, which isn't ideal, but let's worry about that later. So array size plus I. What we want to do. Okay. So we want to get the address of the elements. So we duplicate the base address of the array. And then we are calling lauf lib memory address add memory address overflow panic in uint, so we're adding to the base address I times, wait, what if the times the element layout? But what if the element layout isn't? I think I know what. So what if the so if we have an array of arrays, then we can't directly store 0 into it. We need to do it recursively. So we compute the address of the thing by using the layout of the element. So lm layout, this is something that we always have. Element type. So we multiply u by the size of the element layout, which isn't quite correct because we might need to round that up using alignment, which gets a nasty bug if we're not doing that. Do I got the function? So like if the size of the thing, like if that's, then there has to be a multiple of the alignment, and somewhere this has to occur, and I don't think we're doing that anywhere else. So when we do offsets, we can't multiply it by size. We need to round that up to alignment, I think. Because that's at a comment here. Invariant, the resulting layout has a size that is a multiple of alignment. And then we don't need to worry about it. So we get the address of the element like so. And then we are initializing that recursively. Element type with an empty initializer. Okay. So that works. If we're having an expression in it, clog unreachable, this is not valid C code. And if we're having a braced in it, it gets tricky again, so let's skip that and try U. So we've got initialized by empty, and this generates a bunch of code. So we are getting the base address. We're adding the offset 0, pushing 0, doing a swap, storing that. Getting the next one, like we're adding add 8 to it, and so on. So this is what I meant with like unrolled loop. But in the end, everything gets initialized to 0. I can do a tiny optimization. If I is 0, then we don't need the add. Okay. To do, or rather fix me, call memset or something instead. Okay. But the tricky thing is the braced initializer. Again. And here we can, I think, just reuse the same logic. But instead of going up until the array size, we are iterating over all lm inits, initializers, keeping track of the index, and instead initializing that particular element using the lm initializer. And then we need to 0 initialize the rest. So let's just copy U. And then we need to sort of fabricate an empty one out of thin air to get it recursively. So let's actually keep you as a to-do so we can see what that on. So 1, 2, 3. Let's see whether that part works. All right, and we're getting 2 out of it, which is great. And we got like the bunch of code in here. That's good. So let's actually then write a memset function. So we want to define a new built-in. Now runtime built-in, which is called love memset. It takes as a single one argument, which is the size in bytes. It takes 2 arguments. So the pointer and the size in bytes. Runtime built-in default. Yeah, default. Name is memset. Okay. So we are getting on top of the stack, we're getting the size, followed by the address. Then we want to get that into memory. Runtime get pointer dereference. What's it called? Get pointer. We want to get the mutable pointer from our process at the base address with the layout specified by the size in bytes and an alignment of 1. And then we want to iterate over then we can essentially call the real memset pointer 0 size. Is that the order? Where did it? Okay. I think that's the real order. Let's just see. So then we memset it, and we subtract 2 from the stack pointer, and then we continue. Runtime built-in dispatch. Right. Size in as a uint and the address as an address. Okay. And then instead of calling memset or something, we're just calling memset. Love Adam call built-in love memset. And we need to get the size. So love Adam int uint b, and the size is the size of the array. Array size times element layout dot size. And then here, when we 0 initialize the rest, we need to call the rest by doing by getting the yeah, that's the logic, I believe. Why are we entering with exit code 2 though? That's a bit... Okay, so let's see when we have an empty array. What happens? We are calling... like the built-in, the printing isn't aware of the built-in, so we just get the address. 18, is that correct? 3 times 8 is 24. 24, yes. So that appears to be correct. I'm just curious about the exit code. Where are we getting exit code to? Where are we getting exit code to from? Return code. Why are you returning 2? You're not supposed to return 2. I think the issue is we're probably leaving something on the stack that we're not supposed to. So we're getting the address, we're pushing something, then we're calling the built-in. This is... Oh, and I think I know what the issue is. When we're calling the built-in without memset, we need to add 2 because the stack goes in the opposite direction. Yeah, okay. So now that one works. Memset, yeah, calling it in the correct order as well. So that's braced initializers for arrays, I believe. What we can make a bit nicer is this thing right here. So instead of duplicating and adding it, we can just keep adding things to the address. So after we're done with one element, then I don't know. So after we're doing codegen for 1, we are incrementing the address by 1. So here then we just need to duplicate it once, because the recursive call will consume the address. So we duplicate it, and then we add the next element to it, and then we implicitly have the thing right here. But I still need the index because I know how many things need to be left initialized. I think I know what I can do. So instead of in the AST, we can keep track of how many are missing. So missing inits, which isn't, they're not missing, they're like implicitly empty or something, right? If there are fewer, the shall be initialized implicitly. Yeah, so let's call it trailing empty inits. So it's the trailing empty inits. Set trailing empty inits. Like so. And then we can just set those in the compiler right here. Init set trailing empty inits array size minus the init count. In that case, and we of course want to initialize u to 0. And then in codegen, I can just do init trailing empty inits, but only if we are having any. Right. And now when I've got like 1 to nothing, seal of print array 0, array 1, array 2, we will get 0, 1, 2, and 0, hopefully. 1, 2, and 0. And right here, we're getting the address. We're doing a bunch of operations. That one. Okay, that one isn't ideal. What's going on here? So we're getting the address of our array. We're duplicating it. We're pushing 1, which is the thing that we want to store. So now the stack contains the address again, and 1. Then we're swapping the 1 and the address. So now the stack contains address, 1, address. And then it realizes, oh, the address is statically known to be a local, so I can remove it and instead call this instruction. So this pop cancels this pick, but due to this swap, this isn't noticeable. So constant evaluation here can do a bit of a better job. But anyways, so we're discarding the address and storing it directly into the address that is a parameter of the instruction. So the store local value directly stores it into the address given in the instruction. Then we're doing an address modification. So we are incrementing it by 8, duplicating it again, getting the value, swapping it to get it in the correct order. And at this point, since we did the pointer arithmetic, constant folding is a bit lost. It doesn't know what to do. So now at this point, we have to dynamically dereferencing it and call the store instruction into field 0. So yeah, then we're calling this magic built-in here at the end after we did, wait. Why are we pushing 8? Oh, that's the size of the thing, right? We want to map set 1. Right. So that's all correct. Now the interesting thing is that yes, we are not handling that. So what happens when we want to do it in global scope? CodeGen global init. So if you have an initializer, we need to do constant evaluation of that initializer. So this is essentially like here we're doing constant eval of an expression, but this could be an expression or an initializer. So let's turn it into a template, expression or init. Expression or init e. And then this isn't, I don't want to like handle all those code duplication. So I'm just doing a bit of type switching here, which isn't, I don't like it, but it works. So if you have an expression, we can code gen it. Otherwise, we are code gen init. Context expression. Oh, we don't having a type. So here we're having a type. Again, we're passing a type right here. So we can pass in a type. Because an initializer doesn't have a type. So then here we want the loaf type of our type. And then we're storing that into the loaf type. And here we want the regular type of our init. And this one first needs the address of our global. So it can store into the address of our global. And then right here we need the layout. Let's store your globally right here, auto layout, code gen layout of that type. Then we can use you right here. And then when we're calling you, we are passing in the type. And we are passing in the init. And then here we are right passing the same thing. And then somewhere right here, where we do u, we need the type of the expression. Cannot initialize a member of blah. Oh, this is expression or init. Hey, and that one still works. And because we did constant folding, we've got 1 right here, then we've got 2, and then we've got 0. So we can also constant fold an initializer. So let's finally commit that. Add initializer support. So we are not quite at the point of the thumbnail where we can do that. But like I've been streaming for 90 minutes, so let's do that next time. Thanks to everybody who stopped by. And until then.